So now, by the same time in history, Hagen and Poiseuille from France, they derive a flow equation. And that has an assumption called a laminar flow. Laminar means sheet-like structure in the flow, and Newtonian fluid. Newtonian fluid, there's a non-Newtonian fluid concept, which means the viscosity stays a constant. It's not function of the velocity. In that regime, we simplify it as a Newtonian fluid. But there are cases for non-Newtonian fluid, which is out of our scope for now, through a cylindrical pipe. So let's see blood vessel as a cylindrical pipe. Then, for the flow to happen, you gotta have a force. In this case, it will exert as a pressure. P1 and P2 difference will make the fluid to flow. Well, think about it. There's a wall. Because of the wall, that wall will drag down the flow. So that wall acts as a resistance. So the resistance to flow is coming from the walls, which is touching the flow. And the driving force is, of course, pressure drop. With this assumption, as I showed you already from previous, the pressure drop throughout this flow will be like delta P is like this. Here, Q is the flow rate, and the other, this is, from this analogy with Ohm's law, this becomes a resistance. So pressure difference between the two ends as a delta P, then this pressure drop will be proportional to the length. So the length of the pipe, so it makes sense. And also think about the viscosity, which is the intrinsic property of dragging resistant to flow, is of course the higher the viscosity is, the higher pressure drop you will need. While the radius, the smaller the radius, the higher pressure drop. Okay, so as a result of viscous forces, the velocity of the flow actually varies across the radius of the pipe. So in this pipe, I have to show you one of this fluid distribution. There, in engineering, there's a well-known condition, so-called no-slip boundary condition, which means when there's a fluid flow, the touching surface and that part, the velocity will remain zero, so it can't move. And a good example is you have, let's say, this surface, like this surface. By just blowing, you can remove all the dust, which especially are stick on the surface because there's no slip condition. So really clean the dust, you have to have real tissue to really swipe to clean the dust which is stick on the surface. So this is called no slip boundary condition. So at the surface, there's a very little or zero velocity, and in the middle, it's higher. So you solve the equation on this, you will get the velocity is maximum at the center, and this velocity profile will look like parabolic shape. So how does this relate to our circulatory system? As we remind you, the resistance is proportional to R to the -4. So the radius will be very important for the pressure drop. So let's have a simple diagram of vascular branching system. We have artery, first order arterial, it will branch out into second order, third order, and fourth order. And it now become about diameter of 10 micron order. And the capillaries is smallest diameter, which is about, only like a couple of micron order. And then it collects into the venule, which means a smaller vein, and the second, third order venule, and it collects into as a big venule and veins. So what about pressure drop related to this? Here is the place where the heart pumps and high pressure arterial blood is coming in. So that pressure drop comes from aorta, and this zigzag is because the heart is pumping, okay? So it goes dramatically down when it becomes to the arterioles, you can see. And also it comes down again through capillary because it has smallest diameter. And because of that, the pressure is very, very low in the vein. And that's why vein is a system, collecting system. Sometimes it needs a valve so that it prevents the backflow. And of course, you can go to pulmonary artery. So axial pressure drops along the blood vessel in the circulatory system. There comes about 80% of pressure drop in the systemic circuit occurs, you can see from here, which is arterial, and here, capillaries.